All right, hello everyone. Today we're going to do section 3.3. I'm going to have to bounce back and forth between my book and my iPad, so bear with me when I do that. And then there's actually going to be a second video today just on a calculator process only. So section 3 talks about linear correlation. So in section 1, we just talked about the strength of a relationship. We use these really vague terms like moderately weak, moderately strong, pretty vague. So we're going to put a measure to that right now. So the first thing I'm going to do, so I don't have to bounce back and forth too many times, is show you a little picture and talk about what correlation is. So correlation, and it's going to be in my notes here in just a second if you're writing stuff down, is the measure of the strength of a linear relationship. So I'm going to put that together again in a second. So what you see here in the book basically are five different graphs. And in section 1, we could have answered the question like describe that: moderately weak, moderately strong, linear, curved, that sort of thing, right? Now we're just going to put a measure on this correlation. So correlation is a formula, which I'll show you in just a second, to measure the strength of the relationship. And it measures just linear relationship. Pretty important to remember that. So the perfect correlation, if everything fell on one line, that would be a correlation of 1 in the positive direction, whichever way it looks like for you there. If it's on a perfect line in the negative direction, it would be -1. So the closer the number is to 1, the stronger the relationship is. And then the difference between like 0.8 and -0.8, those have the same strength. It's not like the negative weaker, it just has a negative trend that goes along with it. So basic idea here is just to match which correlations are which. We have a -0.95, a -0.5, a 0.5, and a 0.95. So I'll walk through this really quickly. So the stronger the relationship, notice C and E are the stronger relationships, more closer to linear. Those are going to have the correlations closer to 1. And then positive trend, so this would be 0.95, and negative trend, this one would be -0.95. And then the weaker ones, a little bit weaker, are these two, or those are going to be the 0.5s. Positive trend here, so 0.5, negative trend here, -0.5, and this one's pretty close to 0, just kind of scattered like an ellipse, an elliptical shape, often has a correlation of 0. So that's kind of the basic understanding of correlation. I'm going to put that together here on my iPad. So, oops, give me a second here. Sorry about that. So the iPad's going to pop up here, and we're going to talk about linear correlation. Okay. So linear correlation is the measure of the strength of a linear relationship. I should type in there, of a linear relationship. Okay, so we don't, if it's curved, we don't put this R to it. Could have an R that goes along with it. Every data set has an R that goes along with it. But we usually wouldn't do that because of the fact that it's not linear. But everything could have some sort of relationship, some sort of correlation. So again, like I just said, that correlation is always between -1 and 1, just kind of repeating stuff. The negative positive just goes along with the trend. And then 1 or -1 would mean a perfect correlation. Okay. So ultimately, I'm going to show you how to find this correlation. So we're not just going to guess. You could estimate one is stronger than another, that type of thing. But there is a formula. And so I'm going to give you the formula right now. It's on your note sheet. And then what I'm going to do in a separate video, just so it's not all lumped together, is go walk through the process on the calculator, just like we did for standard deviation. Just like we did for the line of best fit, finding the slope. So if you remember that process, you could probably pull it out on your own. You can see the formula has the number of data points, n. And then you're just going to take, if you remember from chapter 2, z-scores. Now we're really just multiplying z-scores. So for every point, you find how many standard deviations away from the mean the x value is. So x minus x bar over its standard deviation. And then for that same point, you take the y minus y bar and divide it by its standard deviation. Another way to think about that, to remember, is those are actually just z-scores. So you take each z-score for the x and the y for every point, multiply them together, and then add them all up. So I'm going to put that together using lists, just like we did before. Okay. And R, I guess I shouldn't really say it. R is the letter. I think I put it up here. Sorry about that. R is the letter that we use for correlation. Okay. So again, there'll be a second video that does that. So there's only one other thing before I go to that video, actually. It turns out that there's a relationship between the slope of the regression line and the correlation. You could do this using all these formulas. I'm just going to tell it to you really so you don't have to worry about it. But the slope of the regression line is equal to the correlation times the standard deviation y over the standard deviation of x. Now, we have a way to find the correlation, but if you're given certain information, you can grab it a little bit quicker. So you might see a problem that looks like this. So we have two variables, SAT scores, verbal and math. The average verbal score is 514 with a standard deviation of 113. The average math score is 505 with a standard deviation of 111. And then we're going to tell you that the correlation between those two is 0.7. So that based on that information, we should actually be able to find a line of best fit and then make predictions. So the question might be something like this. Estimate the math score from a verbal score of 600. So I'm going to walk you through that process using this equation. Got the calculator. Calculator, a little math. So remember, in order to find the line of best fit, we need the slope and a point. So we have a point. Oh, sorry about that. I put X bar for both. So right. So the reason I did that, you notice there's an X bar for both. The reason I did that is we have to decide. So the question says estimate a math score from a verbal score. So that means we want to predict the math score from a verbal score. So our line of, whoops, let me just put a space there for the B. Or a line of best fit, it's going to look like that. So now I know which one's Y and which one's X, right? So for me, I always write this out this way. So I know which one's my Y and which one's my X. And then if I use that formula I just gave you on the other page, which I'll write down here again, which is B1 equals R times SY over SX, I can try to find the slope of the line of best fit just from this information only. So the slope would be the correlation times the standard deviation of Y. Remember, Y was math, and math standard deviation is 111. And then the standard deviation for X, which is verbal, is 113. So I grab out my calculator here, 0.7 times 111 divided by 113 gives me a slope of 0.6876. So I'm just going to round it to that, not worry too much about that. And now I have Y equals 0.6876x plus B. And now I can find B the same way we did last section by putting in that point. Remember, the point of average is X bar, Y bar is always on the line of best fit. So my X bar is the verbal, which is 514, and my Y bar is the math, which is 505. So if I go 505 equals 0.6876 times 514 plus B, I'm just going to write this all up at the same time and find my B, 505 minus 0.6876 times 514. So I get B equals, I'm going to write this out for you here, Y equals 0.6876x plus my B, which is 151.5736. And now the original question, remember, was to predict the math score from a verbal score of 600. So now I just come in here, Y equals 0.6876 times 600 plus the 151.5736. So that's sitting there right now. So plus 600 times 0.6876 gives me a score of roughly 560. Whoa, sorry about that. 564 with a little rounding. All right, that's about it. Just one thing. I'm using this term relationship. And correlation is just a relationship. It tells you how strong the relationship is, but it doesn't say anything about what's causing something to happen. So it doesn't say that one's causing the other. It might be that one's causing the other. We have other things that we have to do to prove those things, like experiments. We'll talk about chapter 4. But just really, really caution that correlation does not imply one's causing the other. There's often what we call these things called lurking variables, my favorite term, kind of that could be the reason for that relationship, which you'll see in the homework problems tonight. But just because the correlation is super strong, like 0.9, 0.8, and we didn't really even say like what's super strong. Okay, we'll leave that for later. But if 0.9 you might think is super strong like that picture showed, doesn't mean that one's causing the other. So pop over to the second video. I'm going to just specifically show you how to find this correlation using this formula and using the list on the calculator, just like I did for the line of best fit. But if you felt good with that, you'll probably be okay with this and maybe even be able to try it on your own. So see you in the next video.